another Learning Together session with Russie's Brosis Foundation. I am so delighted to have you with us this evening, as always. And we have something very exciting in store for you today. The last time we were together, we were practicing how to write arithmetic sequences, geometric sequences, and also I introduced you to the Fibonacci sequence, which is a very unique sequence, but I want you to be able to recognize that it does exist. And many times people mention it and puzzle a lot of people, but you won't be puzzled because you know what it is now. Today, instead of just talking about a sequence of numbers, we're going to find out how we can expeditiously add the number of terms that we specify. For example, I could say, what is the sum of the first 50 terms of an arithmetic sequence? And we need to find a way that we don't have to just add the first, the second, the third, the fourth, the fifth. It becomes tedious after a while. We need to find, as problem solvers, a way that we could find the sum in a strategic manner and also a very efficient manner. So that's where we're going today, finding the sum of arithmetic sequences and also geometric sequences. And whenever we transition into doing the sum, we're now looking at what we call not sequences, but we're looking at series. Okay? So a sequence is a list. A series is a sum of the list. Okay? So let's remind ourselves of the arithmetic sequence, and I'm going to do the arithmetic series. So the arithmetic sequence is where you have the first term, the second term, the third term, the fourth term, okay? And now, if we're asked for the arithmetic series, so the arithmetic is really A plus D plus A plus 2D plus A plus 3D plus etc., etc. And with the arithmetic series, we're looking to find a way that we could add a specific number of terms. I could say, what is the sum of the first 100 terms? Or later on, we're going to see if we were to ask you, what is the sum of the 80th term to the 200th term? So we just want only a portion, not from the beginning, but from somewhere in the sequence, okay? So we're going to explore those possibilities. So let's get to work. We are going to, instead of me giving you the formula, we're going to develop the formula, which is a pretty neat approach. We're going to actually develop and see where the formula came from. Pretty cool? Yes, I think you will like that. Rather than me just telling you, this is a formula. When you can see where it came from, it will register with you and it will also have much more meaning. So what I'm going to do is I'm going to demonstrate the concept that builds into the formula. So let's use, I'm going to give a sequence and we're going to try and add the first 10 terms of the sequence. So let's use the letter S for sum, and let's use the subscript 10 to say it's the sum of the first 10 terms, okay? And let's use a sequence that has something like this. Say, keep it simple. 1 plus 3 plus 5 plus 7 plus 9 plus 11 plus 13 plus 15. How many do we have? 1, 2, 3, 4, 5, 6, 7, 8, plus 17 plus 19. So let's go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Beautiful. We have 10 terms. Now, look at this carefully. Watch this. I'm going to write the same sequence, and this is really exciting. I'm really excited about this. I'm going to write the same set of numbers, but I'm going to reverse the order. So I'm going to instead write 19 plus 17 plus 15 plus 13 plus 11 plus 9 plus 7 plus 5 plus 3 plus 1. So this is the sum of the first 10. This is the sum of the first 10. It doesn't matter if we start adding from the first or adding from the last. You should get the same result. It does not matter. The order does not matter when you're doing addition. And that's what also called the commutative property. When A plus B is equal to B plus A, the order doesn't matter. It's a commutative property. Okay? So check this out. Do you notice that if I added this and this, what do I get? 20. Added this and this, what do I get? 20, 20, 20, 20. If I add these together, do you agree that we're going to end up with 10 sets of 20? So this is going to be 2 times the sum of the first 10. It's double the sum of the first 10. It's actually equal to 10 times 1 plus 19. This is 20, this is 20, this is 20, all of this is 20. Okay? And therefore, the sum S10 is going to be equal to 10 over 2 times 1 plus 19. Oops. Which is equal to 10 over 2 is 5. So it's 5 times 20. And in this case, we end up with 100. So let's recap what just happened. I wrote out the first 10 terms. Then I also wrote out the sum of the first 10 terms, but I wrote the last one first. And I realized that the last term plus the first term is the same as the second to last and the second, the third to last and the third, the fourth to last and the fourth. They all give you the same total. And since there are 10 items at the top, 10 items at the bottom, we end up with 10 sets of 20. So it's 10 times 20. So it's 10 times the first plus the last. And it's going to give you double the sum we're looking for. So to find just the sum of the 10, we have to divide by 2. And there we divided by 2. So 10 divided by 2 is 5. 1 plus 19 is 20. 5 times 20 is 100. So I think you're starting to get what the formula looks like. Let's try another one and see if it really, really works. Let's try another example. This time, let's use a smaller number just for the space. Let's use S8. And this time, let's do a decreasing sequence. Why not? Let's go 50 plus 45 plus 40 plus 35 plus 30 plus 25 plus 20 plus 15. How many is that? 1, 2, 3, 4, 5, 6, 7, 8. Good. Okay. If I do S8, okay, that's going to give me 15. This time I'm writing it backwards. So it's 15 plus 20 plus 25 plus 30 plus 35 plus 40 plus 45 plus 50. All I did, I rewrote the series, but in reverse order. And so it's the same sum. When I add the two sums together, we end up with 2 times the sum of the first 8 terms is going to be equal to, let's see what happened. 50 plus 15, 65. 45 plus 20, 65. 40 plus 25, 65. 35 plus 30, and if you go all the way through 15 plus 50, 65. So we get 65 8 times. 1, 2, 3, 8 times. So it's going to be equal to 8 times the first plus the last. Okay, and that's double, but you only need the sum of the first 8 terms. So we have to divide by 2. So you end up with 8 over 2 times, and 50 plus 15 is 65. So therefore, 8 over 2 is 4 times 65, which happens to be 4 times 5 is 20. 4 times 6 is 24. So that is 260. So look how we got 260 without adding this plus 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 this. You see? So that's monotonous. That's time consuming. We need strategies to expedite the process. And there it is. So by now, I think you're starting to see in your head what the formula looks like. What did we end up doing? We discovered that it's the number of terms, notice 8 terms, the number of terms divided by 2, the number of terms divided by 2 times the first term plus the last term. The first term plus the last term, and that gives us the result. So can we write the formula? Maybe we could write the formula so we can start looking at it now. So, it looks here like the sum of n terms, sum of n terms is equal to n over 2, whatever the number of terms is, okay, times the first plus the last. So the sum of the first n terms, like for the sum of the first 100 terms of an arithmetic series would be 100 over 2 times the first term plus the last term. And that is going to give you the answer. So let's do an example. An arithmetic sequence as A, where A we know is the first term, as 7, and D, where D is the common difference, as 3. And our task is to find the sum of the first 100 terms. So without having this method, how would we do this? Well, we would take the sequence 7, write out the first 100 items in that sequence. So it will be 7, 10, 13, 7 plus 10 plus 13 plus 16 plus 19 plus 22, da 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 da, until we get to the 100th term, and then we just add them, until eventually, like next week, we get our answer. Not next week, but I just wanted to exaggerate. Whereas as mathematicians, we say, no. We're more sophisticated than that. We can get our answer without going through all that tedious, time-consuming process. So let's go. We say, okay, the first term, f, is equal to 7. Okay, the last term is going to be equal to a plus n minus 1 times d. Remember, that's what we did from the last session we had on on sequences. We learned that to get a term in a sequence, we take the first, in an arithmetic sequence, we take the first term plus n minus 1. So if it's 100 term, it's going to be 99 times the common difference. So it's going to be 7 plus 100 minus 1 times 3 equal to 7 plus 99 times 3 equal to 7 plus 300 take away 3 is 297. And that gives us 297 plus 7 gives me 304. So my last term is 304. You might be wondering, 3 times 9 is 27, 3 times 9 is 27 plus 229. But I didn't do it like that. I said 3 times 100 is 300, and 3 times 1 is 3, so 300 take away 3 is 297. So now the sum of the first 100 terms is going to be equal to 100 over 2 times the first plus the last. So it's 100 over 2 times the first, which is 7, plus the last, which is 304. So that is 50 times 311, which gives me 0, 5 ones 5, 5 ones 5, 5 3s 15. Wow, how cool is that? Look at that. I think that's a very nice question. An arithmetic sequence starts at 7 and has a common difference of 3. Find the sum of the first 100 terms. And what did we do? We say, okay, the first term is 7, and we have a method to find the last term, to find the nth term. This is the nth term. And in this case, our nth term is 100th term. That's our last term, okay, because I want the sum of the first 100. Okay, it's the first term plus whatever the number is minus 1. So it's 100 minus 1 times the common difference, which is 3. And we end up with a last term of 304. And then we go ahead and we say, oh, okay, it's 100 over 2 times f plus l. 100 over 2 times 7 plus 304. 304 and 7 is 311. 100 over 2 is 50. 50 times 311. 15,550. Now, this formula that is here is the most simplistic version of the formula. But I'm going to show it to you in a more sophisticated manner. But it's the same formula. Take a look. So many teachers could just easily just give you the formula and say, this is what it is, do it. But I'm trying to give you a feel, sort of like a little ownership as to where this thing is coming from. Because when you start to see how these things evolve, they'll become more meaningful. Okay? So we already showed you that the first and the last work, okay? And of course, we agree that the first term is also referred to as A. The last term is always equal to A plus n minus 1 times D. So what I'm going to do is I'm going to substitute for F and substitute for L in that formula. So Sn is equal to n over 2 times your first term is A plus your second term, your last term is A plus n minus 1 times D. Let's simplify that. It's equal to n over 2 times A plus A is 2A plus n minus 1 D. So this is, truthfully, this is the more common formula for the sum of an arithmetic sequence, the sum of the first n terms of an arithmetic sequence. But this is really where it's coming from. It's the first plus the last times n over 2. That's where it's coming from. Okay? So let's see if we could use this formula the way it is right here with the detail that we were given and see if it works. So what were we asked? We were told that A is 7, N is 100, okay, and D is 3. So the sum of the first 100 terms is going to be equal to 100 over 2. That's it, 100 over 2 times 2 times A, which is 7, plus 100 minus 1 times 3, and close parentheses. So it's equal to 50 times 2 times 7 is 14, and 3 times 99 is equal to 3 9 is 27, so it's 297. Okay, so it's going to be 50 times 14, and 4 plus 7 is 11. 1 and 1, 2 and 9 is 11, so it's 311. And then we multiply these two, we end up with 0. 5 1's 5, 5 1's 5, 5 3 is 15. So what did we end up with? Same answer as before. Okay? Now I'm going to take one more step and show you how this formula came about without even using this. Okay? This one you have to put your seatbelts on because this one is a little bit more sophisticated. But I just wanted to share it with you just in case you want a little mental exercise. You can close your eyes or you can just stay with me, but I'm going to quickly go through this for you. So, what is the sum of a general arithmetic sequence? Well, the sum of the first n terms is going to be equal to A plus D plus A plus 2D. So this is your first term, second term, third term, plus A plus 3D plus A. The last term is going to be A plus N minus 1 times D. A plus N minus 1 times D. That's the last term. Okay? And I'm going to write it again. But this time, I'm going to write the last term first. What do we end up with? We end up with a plus n minus 1 d plus the one before this, that is the second to last term, is going to be a plus n minus 2 d. The third to last term is going to be a plus n minus 3 d plus, and as we come to the first, we're going to do plus a. When we add these two terms together, we get 2 times s of n. What is that going to be equal to? I will prove to you that this plus this is the same as this plus this is the same as this plus this. I'll prove it. Okay? So let's do a sidebar and see what happens. So the first, this plus this is going to be a plus n minus 1 times d. This is a plus n minus 1 times d plus a. What is that equal to? A plus a is 2a plus n minus 1 d. So that's what I got for the first and the last. Let's go for the second and the second to last. Let's see what we get. Here we go. A plus d, that's it right here, a plus d plus a plus n minus 2 d. In order to appreciate this, I'm going to have to expand so I could combine like terms. A plus a is 2a. And then plus, there's a d. And then this times this is plus nd minus 2d. So it's equal to 2a is here, d minus 2d is just plus, you have the nd minus d. Factor out a d from here, we end up with n minus 1 d. Is this the same as that? 2a plus n minus 1 d, absolutely. Okay, let's try the last one. Let's try this and this. And by then, well, let's try this and this, sorry. This and this. This is enough to be the third, okay, and the third to last. So here we go. We already proved that this is the same as that. So I need a little space to work with. So let me erase this one right here. So the third and the third to last. The third and the third to last. Here we go. So the third is a plus 2d. Plus the third to last is a plus n minus 3d. We're going to distribute and we're going to combine like terms. So it's 2a plus 2d plus nd minus 3d. So 2a, 2d minus 3d, we end up with minus d. And then of course it's 2a plus, factor out a d, we end up with n minus 1 times d. Look at this, d times n and d. D times negative 1, negative d. This is the same as that. So we realize that we're going to get this plus this is the same as this plus this is the same as this plus this all the way through to the end. How many terms do we have? We have n terms. So therefore, right here, we can say it's going to be n times this expression, 2a plus n minus 1 times d. And what we're looking for, we're looking for just the sum. So we have to get rid of the 2 So we divide both sides by 2. And now we end up with 2a plus n minus 1d. And that is the formula that I was telling you about. This is it, which is the same as n over 2 times the first plus the last. Okay? So let's do one more example, and then we transition over into geometric series. Okay, let's do one more example. Okay, so this time, instead of saying to you, find the sum of the first 50 terms, I'm going to switch it up a little bit. Instead of the first 50 terms, let's say find the sum of the 30th to the 60th term. Now let's try the 31st. Given find let's make sure we understand what's at play. So I give you a sequence. And I say, find the sum of the 31st to the 50th terms. So 31, term number 31, 32, 33, 34, all the way up to term number 50. Okay? So how do we do that? Because the formula that we have is talking about finding the sum of the first n terms. We know that is equal to n over 2 times 2 times the first term plus n minus 1 times d. Suppose we found the sum of the first 30 terms, and then we found the sum of the first 50 terms. Do you realize that if we subtracted the sum of the first 30 from the sum of the first 50, then it would get rid of and just leave you with the 31st to the 50th. So that's how you do it. You find two sums and subtract the first few terms from the last terms. So here we go. So S30. So I'm going to do S30, and I'm going to do S50, and I'm going to subtract S30 from S50. And that will answer that question. So S30 is going to be equal to 30 over 2 times 2 times the first term, which is 200, plus n is 30 minus 1 times the common difference in this case is -2. You did see that it's a decreasing sequence. It's going down by 2 each time. Okay, so what do we have? It's equal to 15 times, this is 400. Okay, and this is going to be 29 times -2 is -58. So 400 minus 58. Okay, so it's equal to 15 times 342. And I'm not going to do that in my head because time is against us. So let's get it right. And let's go. So it's 15 times 342. 342 equal to 5130. And a double check. 15 times 342 is 5130. That's correct. Okay, so let's go to the next one. So S50 is going to be equal to 50 over 2 times 2 times 200 plus 50 minus 1 times negative 2. So it's 25 times 400. Okay, and then 50 minus 1 is 49 times negative 2 is 98. Is minus 98. And what does that give us? 25 times 302 equal to 25 times 302 equal to 7550. Let me double check. 25 times 302 equal to 7. So the sum of the first 50 terms is 7,550. The sum of the first 30 terms is 5,130. So the sum of the 31st to the 50th, I'm going to say sum needed equal to 7550 minus 5130. And that's going to give us 0242. The answer is 2,420. Okay, so what's another way that we could have done this? Well, another way we could have done this is find the first, which is the 31st term, find the 50th term, and use the first and the last, and find the answer. So let's try and do that. So the magic number is 2420. That's our magic number. If I found the 31st term, and I found the 50th term, and I use the principle n over 2 times the first and the last, it should work. Okay? So let's try that quickly and see if we get the same answer. Okay, so here we go. So the first term is going to be term number 31st. Is equal to 200 plus 31 minus 1 times negative 2. Okay, so it's equal to 200 plus 30 and negative 2, which is equal to 140. Okay, last. And that, of course, is term number is the 50th term. Is going to be equal to 200 plus 50 minus 1 times negative 2 is equal to 200 plus 49 times negative 2. That's going to give you negative 98. That gives you 102. Okay? So the sum from the 31st to the 50th is 20. You're gonna have 20 terms, 31, 32, 33, all the way up to the 50th. So S20 is gonna be equal to 20 over 2 times the first plus the last. So it's equal to 20 over 2 times, what's the first? 140. Plus what's the last? 102. So it's equal to 20 over 2 is 10 times 140 plus 102 is 242. And 10 times 242 is 2420. Did you see that we ended up with the same answer that we had before? Isn't it beautiful? And that's one of the beautiful things about math, that if your method is correct mathematically, then you should get the same answer. If you get a different answer, it's either you made a mistake or your method is wrong. Okay? Good. So now we have exhausted arithmetic sequence, but I thought that was very good. So let's go to geometric sequences now and see if we could add the terms of a geometric sequence. Now you know why I did not do sequences and series the same session, because you see how involved this can get. Okay, so sequences was like an introduction. Now that we're doing the series, it takes you up to another level of demand or rigor. Okay? So we're going to go to geometric. Okay, just as a reminder, a geometric sequence is one in which consecutive terms are obtained by multiplying by a common ratio R. So we're going to see the sequence, the geometric sequence is AR squared, AR to the third, AR to the fourth, and then comma AR to the n minus 1. So that's what the geometric sequence is. And for the geometric series, just remove the comma, which gives you a list, and put plus, 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 plus. So now we're adding the terms of a geometric sequence, and that's how you get a geometric series. Got it? Now, the formula for the sum of the first n terms of a geometric series is not as straightforward as for an arithmetic. But if you hang with me, I can show you the process. So now you have had some muscles developed, you will be able to take this ride with me. So let's be patient. Okay. What I'm going to do is, I'm going to illustrate by just using a specific geometric sequence, and then we'll transition over into the more abstract general geometric sequence. So I'm going to see how we add the terms of a given sequence, say for example the first 8 terms, and then see if we can expand that thought process. So given 1, 3, 9, find S8. So this is your geometric sequence. I'm asking us to find the sum of the first 8 terms. Very interesting. Okay. 1, 2, 3, 4, 5, 6. Okay. So what we'll have to do is we'll have to write it. Okay. It's not gonna, I think I'll have to just go to the formula because it's not gonna be as easy. Well, let's try. Let's try. So here we go. So S8 is going to be equal to 1 plus 3 plus 9 plus 27 plus 81 plus 243 plus 3 3 is 9 and 3 4 is 12, 3 2 6 and 1 is 7 plus 3 9 is 27, 3 2 6, 3 7 is 21. Okay? And now we have to go to the, it's not gonna work. I think I have to go with the formula. I have to create the formula for us. I think it's gonna be easier that way because it gets very confusing fast if I try to go from here. So the sum of this would be, well, what I'll do then, I'll just go ahead and add them and see what it comes up to. And then later on, we'll go back using the formula and see if we get the same answer. Yeah, that's a good compromise. So 1 plus 3 is 4, and 9, 13, and that's 40. Plus this is 4, and that is 32. Plus this 9 and 7 is 16, 2, 10, 11. 7, 1, 8, and 1, 9. So let's check. Let's double check to see if I'm correct. 1 and 9 is 10, plus 3 is 13, and 27 is 40. 1 and 3 is 4, 8 and 24 is 32. 9 and 7, 16, 2 and 8, 10 and 1, 11. 1 and 1, 2 and 7 is 9, and 2 comes over. Okay. So let's add these together. 6 plus 4 plus 0 is 10. 1 and 1, 2, 4, 8. 9, 12, and then 1 and 2 is 3. So I'm getting 3,280 as the answer for this. 3,280. I want to double check quickly to make sure we're correct. So this is going to be 364, 0, 8, 2, 3, 2, 8, 0. Yes. Yes, that works. So I'm going to leave this right here, and I'm going to try and develop the formula. And then we can see if when we use the formula, we end up with that answer right there. So here we go. Sn is equal to A plus AR plus AR squared plus AR to the third plus. And the last term is AR to the n minus 1. So let's multiply the entire equation by R. So R times Sn is equal to, when you multiply this by R, we get AR. When you multiply this by R, we get AR squared, AR cubed, AR to the fourth, plus. And we're going to get 1 before this is going to be A plus AR to the n minus 1 plus, and the last term is going to be AR to the n. Because when we multiply this by R, it's going to be add 1 to this, is n minus 1 plus 1 gives you just n. Okay? Now, watch this carefully. If I subtract this from this, what do we end up with? We end up with R Sn take away Sn. So just mentally see if you could think of taking this from this. You realize that we're going to end up with this is going to cancel this. This is going to cancel this. This is going to cancel this. All these will cancel each other. This is going to cancel this. And this is going to be left. So there's no match for that one. There's no match for this. So you end up with a r to the n minus a. When you subtract, all the middle terms cancel out each other. Okay, this and these will all cancel. And you're left with the first and the last. Okay, now look at this. We can factor out Sn. So we get r minus 1. And factor out a. It's going to be a times r to the n minus 1. And now we can get the sum by itself by getting rid of the r minus 1. We divide both sides by r minus 1. We end up with the sum is equal to a times r to the n minus 1 all over what is in the parentheses, which is r minus 1. So what's the answer? The sum of the first n terms of an arithmetic, of a geometric series is the first term times a common ratio to the power n minus 1 divided by the common ratio minus 1. Okay? So now we're going to go to this example that we had before. N was 8, A was 1, and R was 3. Okay? So now we're going to find, using the formula, S8 is equal to A, which is 1, times R, which is 3, to the power 8, minus 1, all over R, which is 3, minus 1. So this one does make a difference. What is 3 to the power 8? Get your calculator, and we go. Clear, it's 3 carat. You know the symbol carat is 3 carat like a tenth to the power 8. And that will give you 3 carat 8 gives you the number 6561. So it's 6561 minus 1. And what are we dividing by? We're dividing by 3 minus 1 gives me 2. Okay? What does that become? When you subtract 1 from here, we end up with 6560 divided by 2. And what is that? 2 into 6 goes 3. 2 into 5 goes 2. 2 into 16 goes 8. 2 into 0 goes 0. What's the number? 3280. 3280. Yes, we did it. Okay? So, doesn't this look beautiful? Look at this. Don't you feel like you're in college? Again, I could have just thrown the formula at you. You'll be turned off and said, forget this is too much to learn. But now when I show you that the formula really came by listing the terms, adding the terms, and then we multiply each term by the letter R. So R times the sum is equal to R times each item. And then we subtract. Oh, by the way, we could have subtracted this from the above. It would still give you the same answer. It would be the same result. It doesn't matter if you subtract this from this or if you subtract this from this. All that happens is that if you subtract this from this, it will be 1 minus R to the n over 1 minus R. That's all. It will just flip around. Okay? So let's go to a couple examples now where we could use the formula. So again, the formula is Sn equal to A times R to the n minus 1 over R minus 1. So let me pull an example from this. I have a cheat sheet with some examples. Okay. Find the sum of the first 12 terms of let's use a simple example, and then we can do a more difficult example. So in this case, we're going to use 7, 14, 28, 56. Okay, so A is equal to 7, R is equal to 2, and N is equal to 12. So S12 is equal to A, which is 7, times R, which is 2, to the N, which is 12. So since we're using parentheses inside of parentheses, let's elevate to a square bracket. It just looks better. So it's that minus 1 over, the bottom is going to be 2 minus 1. That's your R minus 1. And what does that work out to be? It's going to be 7 times, what is 2 to the power 12? 2 caret 12 gives us 4096. Minus 1, see the minus 1, over 2 minus 1 is 1. So do you see that it's going to be 7 times 4095. So therefore it's going to be 7 times 4095. And that's equal to 28,665. I think that's a pretty cool skill to have. Instead of having to write out all these numbers, all 12 of them, and getting your calculator and add, somebody could say, okay, what's the sum of the first 50 terms? You'll be doing the same thing over and over for a long time. Whereas if you have a method, you could quickly go to your result. And that's what we have just done. Okay, so let's try something that's a little bit uglier. Let's try that. Oh, one last question. Okay, so find the sum of the first 10. Sum of the first 10 terms of 729, negative 243, 81, negative 27. Of course, it's going to be okay. So what do we see here? A is 729. Your R is negative 1/3. If you divide this by this, you get negative 1/3. This by this, negative 1/3. This by this by this, negative 1/3 all the way through. And your N is going to be 10. So S10 is going to be equal to 729 times the R. Okay, you're going to have to use parentheses. So it's going to be negative 1/3 to the power of 10 minus 1 over R, which is negative 1/3 minus 1. So it's ugly, but it can be done. So what do we end up with? It's going to be equal to 729 times negative 1/3. Oops. To the power 10 minus 1 over, and this is going to be equal to negative 4/3. Negative 4/3. So when we flip that, what do we end up with? Okay, when we flip that, well, it's negative 4/3. So dividing by a fraction means that you're going to flip and multiply. So I'm going to go ahead and put everything into the calculator and let the calculator do the work for us. So here we go. So it's 729. First of all, I'm going to multiply by negative 3/4. Multiply by negative 3 divided by 4 equal to, we have one number, and we're going to multiply this now times, open parentheses, okay, and now it's another square parentheses, negative 1 divided by 3, close parentheses, caret 10, okay, minus 1, close parentheses. And the answer is 546. 546.74. And that's an approximate because it's more decimal places, so it's approximately that to 2 decimal places. So that's your answer. So even though you start off with 729, you have negatives and positives, negative and positives. So that's why you end up with a number that is less than 700. Okay? And just to close, I want to share with you that the sum, there is a symbol used for sum, and the symbol it's called the summation. What does this mean? This is actually to find the sum of this expression starting with when n is equal to 1 all the way to when n is equal to 15. So it's a sum starting at the beginning to the end, or starting with the first term all the way to the 15th term. So this is a summation symbol. If I gave you this, and I gave you, say, 1 and 30, I'm asking for the sum of the first 30 terms, okay? And usually, it's usually n that is here, because n is your counter, first, second, third, fourth. So I just want to mention the summation system. So series use summation, okay? And what did we do today? Well, last week we did the sequences. We did the arithmetic sequence, the geometric sequence, and also, well, general, because there are many arithmetic sequences and there are many geometric sequences. And also we mentioned the Fibonacci sequence, which is a very unique sequence. This week we studied how to add any number of terms of an arithmetic series, okay? Which is just the addition of the terms of an arithmetic sequence. And we did the same thing for geometric sequences. We add the terms of the geometric sequences, okay? So with those two formulas, you're well set. You can do lots of damage with adding terms of sequences, especially if they're arithmetic and geometric. Again, on behalf of the Brosis Foundation, I thank you for joining us, and I do hope that this was a little exercise in rigor, academic or intellectual rigor, and you also found it also not just rigor, but also intriguing, because you never knew that you could do these type of additions in such a quick way. For example, if I was to ask you, how do you quickly add the first 100 numbers? Are you going to go add them one by one? Or are you going to go quick formula and say, oh, it's an arithmetic sequence, and apply the formula and get your result? Thank you so much for joining us. And on behalf of the Brosis Foundation, we say thank you for this Learning Together session. Enjoy the rest of your day.